Oh, yeah?
Okay. Welcome to Thermodynamics. We are coming up on this ugly topic of entropy. And the only thing that makes it ugly is it's the least intuitive property that we deal with. And it turns out that it unlocked a lot of secrets of thermodynamics and made it possible to analyze stuff. So first we have to define what it is, and then we'll talk about how we use it. This has to do with that. There's the fourth property of there was constant pressure, constant temperature, constant volume, and then sort of this constant heat flow, no heat flow in or out, insulated sort of a thing. And that's what we're here to talk about. When we're done talking about this, then we can launch into actually talking about some thermodynamics. So, what is this entropy thing? I'm still trying to get into the brains of the guys that came up with it. Rudolf Clausius was one of the people. He probably named things like entropy and enthalpy. But it's 1865, he thought of this stuff. And what if, and this gets to the core of what is the quality of the energy, not just how much do you have. The first law of thermodynamics says how much energy is what matters. We're going to balance that, and it always goes around. But as far as efficiencies, you can't generate the same amount of power on a swimming pool full of water at 85 degrees Fahrenheit as you can with a gallon of gasoline that could have created that heat. It's the same amount of heat, but it's not as useful. So I had to come up with, this looks like calculus. It's more a conceptual thing, but for this circle around the integral sign, this means around an entire cycle. If you go through all of the processes in the cycle, the change in heat, that's a partial differential thing, and then change in the heat flow divided by the temperature at which it happens is always going to be equal to or greater than 0. 0 is greater than, which makes that sign look backwards. Entropy, basically, entropy can only increase. In the ideal perfect world, it could stay the same, but it's always going to increase. So that's the whole thing about reversible process. When you're done, it would come all the way back to the same state. Well, in the real world, you know that if you slosh water in a bathtub and it all comes back, it doesn't come back. You know, you still have the little rubber ducky instead of, if you took that bathtub with the rubber ducky and you let it go down and then you brought it back up, the rubber ducky moves. And so it's not exactly the same. On thermodynamic scales, the same thing happens with the motion of the molecules. But what we really need to, this is equal to S. So a version of the second law, which again, there's a bunch of there's all kinds of definitions of the second law of thermodynamics, but to me what it all means is not only is there a quantity to energy that you're balancing, but there's a quality to it, and some things you can't convert as easily, forms of energy. So that's the entropy is how we measure the quality. So the entropy of an isolated system during a process, always a process being a cycle of, well, it could be an individual process between two states, always increases. In the limiting case of a reversible process, it might remain constant, but it will never get smaller. And we actually use, this is what we're going to be able to use to grab hold of processes and say, the steam went into a turbine, when it came out, best case is the value of entropy stayed the same, an isentropic process. That's adiabatic and reversible. So it's insulated, and it happened in such a way as the little rubber ducky comes back to the same place, which won't really happen. But it turns out this tells us how much energy was there that was available to be converted. You couldn't convert more than that. And now you take a real system and say we only converted 80% of what was available to be converted. There's also exhaust, but that exhaust was at a low enough quality that it wasn't going to help make the engine turn any faster or what have you. You can only, the entropy tells us where the bottom is on the energy that's available to actually cause conversion. So an ideal process equals 0. We use that to find how much energy was available to be converted, and then if we have an actual output state, we can say a particular device is able to convert 80% of, not of the total energy, but of an isentropic process, how much is available, and the rest of that energy just wasn't a high enough grade to be converted. And entropy tells us that quality of, how well can we convert it. So there's two ways, and let's also talk about what it means. So poets use the word entropy for entirely different reasons, but it's kind of the same sort of thing. Entropy, they say, measure a disorder or randomness at the molecular level. If you let molecules expand and then compress them together, they get into some disarray. There's things that go on. So it's actually so a low entropy change in a process, it means you got high efficiency. Yeah. And then there's a third law of thermodynamics, which you probably don't even need to worry about, but the reference state for zero entropy. Remember, we had a reference state in all our tables. It wasn't necessarily a zero energy. It's just at that state, like a steam table, you're not going to have steam that's formed from water at freezing temperature. So we just called that our zero. For entropy, if you have a perfect crystal in perfect order, and it's at 0 degrees Kelvin, then entropy value is 0. I don't know how that's relevant to what we do, but that's the definition. It's perfectly ordered. There's the Q values are there's a 0 Q at that point. There's zero temperature. So again, we have reference states. So that was the third law or fourth law or whatever, whichever law. We won't really have to worry about that law so much. Other than it helps us define this other stuff. So for a steam table, they're going to set a reference value of entropy of 0 at liquid water at
entropy is S?
S is going to be what we see they're using for entropy. And for the R134 tables, they also go to the same place where they have a 0 value for internal energy, 0 for entropy, because the internal energy is where that's part of the, let's look at this. Here's the steam table, or R134 table, and you'll notice here's enthalpy, and saturated liquid enthalpy for refrigerant starts at -40. They figure you're not going to use this refrigerant for temperatures below -40 degrees C, which is plenty cold. And likewise, at this point there's no heat flow. If you take this amount of energy and you divide it, so the saturated vapor, it's really, again, this is the liquid table, this is the vapor table. So vapor 0. Liquid here, we have this many kilojoules per kilogram. Enthalpy was defined as the amount of heat energy transferring in or out of a system at a temperature, at a given temperature. So this is at minus 40 C, which would be 233, 233 Kelvin. It's 40 degrees below 0 and 270. I think if you took 233, if you divide this by 233, you'll get this value. Because at that temperature, this much heat went in the system to create that vapor. So that's where this number comes from. And then if you take the amount of heat it took to go to this, and you divide by, this temperature at which that heat went from this to here, you added some heat to this value, got a little bit of more heat, and you added it. That change, divide by temperature, add it to this number, you get that number. Is that right? Why is that going down? I don't know. I know how this one works. That's my problem with these tables is if I understood them well enough to reproduce them, I could tell you exactly what's going on, but I know for this one, it's about sort of this entropy thing. Yeah. So, for the steam or refrigeration table, something where there's phase change going on, or you're close enough to the phase change thing that it distorts the ideal gas law, then you get all your values off the tables. And now we can use this entire table. This is the one column we've been ignoring, but now this column is going to be something that we use. Because basically what comes down to is if we found, especially in the it's also in the superheat tables, if at superheat we found the input to a turbine had a certain entropy value, and then the output, we know it went down to some pressure, it's a saturation pressure. We can look for that same entropy value, and then we can find out what the quality was there, and then use that quality to find the output enthalpy, and the difference in enthalpy from the top to the bottom tells us how much was available to the turbine to convert. Now,
so the unit is kilojoules divided by kilograms times Kelvin?
Yeah, these are both downstairs.
Right, divided by, sorry. So Kelvin?
Yeah, so it's this, and this comes from that definition.
Okay. Yeah, I remember it's always in Kelvin.
So let's go back to our definition. I want to find, well, our definition basically was a change in S will make the equal thing. In the perfect world, the change is 0. So a change in S would be dQ over T. The amount of heat energy divided by temperature. Or we're going to, it's going to have units of kilojoules per kilogram per degree Kelvin, and that Kelvin's important. It's going to be an absolute temperature, is what they use for it. Interesting thing in the world of ideal gas, we don't have to use tables for it. This is developed in your book, but they're going to use change in enthalpy. So what is the heat flow? So here's the Q. The amount of heat change in a process would be dQ, and the dQ would be C sub P as a function of temperature times dt. So temperature times the C sub P is how much energy that the before and the after on that. That's our dq, divided by the temperature at which it happens. And if you treat this value, we know this will vary over a large temperature range, but if we're a small enough temperature range, you can treat this C sub p as a constant. So they take an average value over that range and treat it like a constant. Then it pulls out and it's the integral of dt over t, which is the natural log of t2 over t1. They're going to pull some tricks on this in a second to make it useful. But an isentropic process would be one where S2 minus S1 equals C sub p natural log of ratio of temperatures. If S2 minus S1 equals 0, there's isentropic. It's insulated and it's reversible because it happens so slow and everything comes back. Then you can say, oh, that's equal to 0. But the C sub p, we can say, was the C sub v dt plus, this is some ideal gas trick. If you remember, C sub p, R is like the work term. C sub v times t plus the work, PV, but PV is R times T. They pulled some tricks on this one. You could also say C sub, it really comes down, there's a chain rule going on here from calculus. And I can reproduce this, but my experience was, unless you're really into the math, you just want to get cut to the chase. And frankly, it would take me a while. I'd have to stumble through it a little bit, but I have done it. There's two ways the chain rule, C sub v plus PV or R for C sub p minus R times the pressure. It has to do with I'll do this much for it, where this is coming from. Oh, I probably shouldn't even do this. When we came up with our definition, oops. Some of our definitions were a change in enthalpy, which would basically the thing that we care about. That tells us everything we need to know. We could say it's a C sub p dt, or we could also say it's a change in enthalpy dH equals D times U plus PV. But if you do that, you get equals du plus d, oops, pdv plus vdp. And that's sort of what's the chain rule on that makes that happen. The pressure times the constant times the change in volume is the word. So this part is called H. And the volume, a constant volume times the change in pressure is not work done. So that's why that chain rule, that issue there, when they mess with it, you have kind of two ways you can define it. C sub V, that's our U, that's the heat, plus this is stand-in for PdV, that's the work part of change in volume and R is essentially yeah. And here's the other one, C sub P, that would be H. Now if you subtract from that the pressure term, constant volume times the change in pressure, that's why this is, it all goes back to that chain rule thing. So, at this point, this is all kind of confusing, I imagine, because I'm not explaining it well. But they're both about, if this is, if it's an isentropic process, and this is all about ideal gas, assuming a constant value for our C sub P, then an isentropic process, this all equals 0. From temperature 1 to temperature 2, pressure 1, pressure 2, state 1 to state 2, whatever the processes are. And I'm sure your book goes through deriving this, but if you think about, there's some tricks they pull with C sub P. If this is 0, then you can say this equals that. If this is 0, you can say this equals like a negative that. And you can take those relationships. It doesn't look like you get there from here, but you get, if that D is, you get a relationship from one of them, you get a relationship between volume and temperature, and there's a C sub V term, and there's an R for the exponent here, and a C sub V on this one. And on the other relationship, you get relationship between temperature and pressure. One has an exponent of C sub P, one has an exponent of R. And then you start playing with the algebra of this stuff, and you can say from this, R equals C sub P minus C sub V. And if you take like the root of C sub V root of both sides here, you can get a relationship of R over C sub V. But C sub P minus C sub V, you start getting these relationships, and you can crank things in here, and this isn't the final form you use. It actually simplifies based on ideal gas, based on a constant value of C sub P, which we know does change, but for a narrow enough range, you can get an average value. To cut to the chase, for the case of ideal gases, taking all that information, combining it, we can for a process that's isentropic, that's reversible, and insulated, that's what isentropic means. Adiabatic is the insulated one. If it's adiabatic, no heat flow in or out, and the other condition is it's reversible. I mean, it happens slow enough that you don't introduce other losses. The relationship between temperatures and pressures and volumes is like this. And it's all about K is the ratio of specific heats, C sub P over C sub V. And that tends to be pretty close to a constant. That does end up being a constant even over temperature. But this now, for an ideal gas situation, this is how we will be able to say between 0.1 and 0.2, what's the temperature out? If we know what the temperature in was, and we know the pressure out and the pressure in, the question is, what's the temperature what's the minimum temperature that'll come out of the turbine. This would also work on your air motor from the lab Thursday. We had air motors that it was expanding, and if we knew the pressure in and the pressure out, we knew the temperature in, we could predict the lowest possible temperature out. And that would be the isentropic temperature. And how much energy was available? Well, it turns out C sub P times the delta temperature is the change in enthalpy. That would be the maximum energy there that was available to be converted. If we measure the actual temperature out, we could then say, with that actual temperature, that, well, it's going to be a little warmer than the isentropic one, because the isentropic said this is how much you could expand to in the best case. And if we got a real temperature out, then we'd say we had this much change in enthalpy, C sub P times actual change in temperature. Thermodynamics says the most we could have done was a wider temperature range, and the H value would be C sub P times the delta, that delta temperature. And the ratio between those two is how efficient our design of our air motor was in converting the energy available to shaft work being done. So that's how this works. Most of the time it's about pressure and temperature. Sometimes, if you want to know what the volume was, specific volume needs to be, then this version of it. Sure. But all of this is coming from these relationships. And where are those coming from? Those are coming from this. If this equals 0, then this equals minus that, or this ratio of temperatures, ratio of pressures. There's a C sub, you can take one of these and these become exponents. You can take a natural log and make that into an exponent. And then if you can move this exponent over there, this one under that one, or that one under this one, and you get the relationship between temperatures and pressures. Here's the relationship between temperatures and volumes. And then all of this stuff you can turn into, R divided by C sub P, or R divided by C sub P gets you stuff you can mess with this K factor on. That's where the K minus 1 over K comes from, ratios of R and C sub P, or C sub P, and then mess with algebra in the exponent. So, all that's well and good. We have two ways to find enthalpy. This one, circle this, if you got this, or write it in your notes, and these relationships you'll be using. For ideal gas law takes care of constant volume, constant pressure, constant temperature, because they're constants. This takes care of that fourth process of insulated, and perfect cases is reversible. This won't be what's real, but it will tell us that limit, how much energy was available to be converted for a turbine or a pump or what have you, a process. If we're doing refrigeration or steam tables, steam turbine refrigeration compressors and things, then it's going to be all in tables. We'll be using tables because they're close enough to the point where some point in the process you've got a phase change going on. This doesn't work for phase change because it distorts the ideal gas law, so we can't use this. By the way, anytime you're using gas law, these are going to be absolute pressures and absolute temperatures. That's crucial. That's usually the mistakes I'll get on exams if somebody uses room temperature gauge pressures. These have to be absolute. values. Now, remember, this enthalpy, it's a measure of the quality of the energy, how useful is the energy being converted. These boxes, again, drives me crazy. These boxes are supposed to be little deltas. So, based on thermodynamic limits, we're talking about calculating this, what is the limit involved, but if you do the actual number and you come up with, for an isentropic process, maybe this one's 0, because we designed it that way, but in reality it comes out, and there is a change in enthalpy, or in entropy, there is a change actually. It'll show up in the tables, it's real when we find that point. It will have increased. You can generate entropy. Remember that entropy was mentioned, randomness, disorder. If your design has, for example, nubs and ridges in it, and when the fluid's going through, even if it was going almost reversible, it goes through there, it starts drifting up, it becomes more random, disorganized, whatever. You're generating, through the design of your device, entropy that causes inefficiency. And it might be unavoidable, it might be avoidable, but something that is one thing that's more efficient than another thing, and less of this going on. It'll show up in the numbers. Whether it's like the veins on a blade are curved better or something. This is something you can control. Basically, what I'm getting at, this is part of the design. You may not be able to you won't be able to get rid of all of it. This is something you can't control. And the total value here is both parts. You can control some of it. You kind of control this if you control your temperatures and pressures. Call it entropy generation. Crummy designs are less efficient. How are they less efficient? Well, you'll find this value. This may not necessarily, you don't want to say, I want to work on this design to reduce the entropy generated. That's not really what you want. You want to make it more efficient. You look at ways to make it more efficient, and this will fall naturally. So, an ideal reversible adiabatic process is isentropic. It has to be adiabatic, it's insulated, and it has to be reversible. Everything comes back to the same place. Usually they talk about quasi-equilibrium. You move it so slow it doesn't know it's moving. That's not going to happen at 3,000 RPM with a 8-cylinder engine or something. So in reality, it's not going to be reversible. But we can measure it against this and say, how efficient is it relative to this ideal state? And that's probably going to be a property of the design. If at a given state you can measure this, then you move it to a different one that's in that ballpark. Your efficiency, how well it does relative to this, is probably going to be really closely related. So if we can measure that ideal state and then say ours is 90% as good as the real state, which tends to be numbers like 80, 90% like it, then that's this isentropic ideal that we can't reach. That's the only way we can grab it and say, the only way we can find that bottom state, the output state. This is all crucial stuff. So, change in entropy is ds is a dq over t. You add that up over a whole cycle. And best case is this can be 0. It almost never happens. In fact, I'm pretty sure it's really close. Really almost never happens. Likely it increases. now we can talk about two different kinds of diagrams. We can talk about a pressure volume diagram, and we can talk about a TS diagram. Now in this diagram, pressure and volume, you can measure both of those. So I can say a change in volume at a given pressure, you change in volume, pressure, got pressure, it moves, that's work being done. Amount of heat flow is integral temperature times ds. Just like we had pressure times volume. So if we have temperature here and ds, we have a little bit of ds at the temperature it happens at, means heat flow. So in one case we're talking about heat flow, and the other one we're talking about the work. If you have a bunch of heat energy, you start off, it causes work to be done. Okay. If you look at this chart, it'll have, on the PV diagram, it's not about heat, it's about pressure and volume. On this one, it's about heat. And this is on a TS diagram, this is what the Carnot cycle looks like. Isentropic, constant temperature. It's a perfect square for a rectangle. At a constant temperature, T ds times all these little ds's, the area from here down to here is equivalent to the amount of heat you put into the system. That's a Q. On the PV diagram, it would be about the work and the expansion and the power stroke or something. From 3 to 4, it's at this temperature. What's happening? It's at constant temperature, but it was shrinking. This was an S value here, T times ds, and you add up all the T ds's from that point to here. This is the exhaust heat that's coming out of the system. And up here, you have this much came in, this much went out. We lost some. We lost that much. This says work net. Really what it is this is the missing heat. And the missing heat turned into work. It pushed something as it was expanding and getting to a lower temperature. So on this diagram, this is really, I should say, Q, delta Q, the missing heat in a TS diagram. It would be the same size as the amount of work that got done in the pressure volume one. They're looking at the exact same thing, and they're in the same units, but in one case, work that got done, in this case, heat that's missing, and the heat that's missing is work that got done. In first law, we're comparing the two. So that's how, that's a conceptual thing of how this entropy, it gives us a window into a graph on the heat flow. So they work together. The entropy is a less intuitive property. It's a combination of the C sub V and the temperatures and all that. It's all about the heat flow instead of about pressure. But it's a way to get a handle on finding, if I knew what this step was, what this was here, and I knew what this temperature was, it's an isentropic process. If this was in the ideal gas realm, which is, most of your engines are using that, I could figure out how much energy was available to the turbine or the piston to change into work. But that's the best case. In reality, it'd probably be a little bit less than that. This gives us a way to grab that number. That's kind of the only way we find it. There's a TS diagram. I won't go into this one too much. You can do the saturation zone on the TS diagram also. For an isentropic process happens slow enough and that there isn't swirls which isn't real. But we can say that if steam comes in with a value of whatever value the input is based on its pressure and temperature off the superheat tables, then if we had an isentropic, if a turbine could get all of it, most, reversible, the most efficient thing could be, then output S2 is going to be the same as the S1. If we know this pressure, we don't know what the temperature is, this relationship helps us go find that output state. That's all of the energy that's available to it to convert. It would be 100% efficient at converting it if it could get to that point for that process. So, and this is the only way we can find that point. We can find it. They can give us an outlet pressure, but we wouldn't know the temperature, or if it's in the saturation zone, we wouldn't know the quality, and we would really all we care about is if we can find the enthalpy point. H1 minus H2, we don't care about the rest, but we can't find H2 without going through finding this S and finding that state, and then we can find the H2 and the difference between them. Enthalpy in minus enthalpy out is the amount of energy available to be converted. That's how we use it. So here's an example. Start off with 5 megapascals and 450 degrees C. That's going to come with a value of S, of entropy. If we have a perfect process, it's going to come out with the same entropy at 1.4 megapascals. But what temperature will that be? Is it in saturation, or I don't know. I have no idea. But the only way I find that point is if I can find at this pressure where we have the same value as it was at S1. And that'll be all of the energy that's available to it to convert. And I don't think I have time. Let's look at charts, and then we'll work on this one next time. But P1's 5 megapascals, T1's 450. So here's 5 megapascals. Saturation's 263. We're at 450, so I know for sure we're in superheat. So 450, come across here, and here's my enthalpy. I want that number. Here's my entropy. At 1.4, we have to find the temperature, the state at which, at 1.4 megapascals, where this is 6.82. H1, I know, and the difference between this value and this is at the new pressure, that's going to tell me. So let's see if we can find 1.46, what was it? 0.82. Move on to 1.4. .82 is going to be between, you have to interpolate between these 2 points, which means it will have expanded. It will drop the temperature from 450 to somewhere like 270 degrees or something. The only way I can find that is finding where this lies between those two. And if I find where it lies between these two, then I can find where it lies between these two. And when I find that value of enthalpy that corresponds to the value of entropy that was the same before, that tells me now from H1 to H2, I'll call H2S because it's isentropic. That value would tell me how much energy was available to be converted in a perfect world. And the real one, maybe we're only do 90% of that difference. So we become an isentropic efficiency, which is what we're talking about now. So that's how we use that. All right, that's it for today.
You planning on the live tomorrow?
Yes,
Bus?
you and